So this talk is on Kani, which is a bit precise REST verifier. It's going to be a joint talk with me and my colleague Celina Val. And we're really interested in sort of engaging with the community here. So please feel free to jump in if you have questions. And then hopefully there'll be some time at the end also for further discussion. So this is RFMIG. And we know that there's sort of a large ecosystem, a large and growing ecosystem of Rust verification techniques and technologies that are out there. And so we think of this as sort of, like a subway map, or for our European colleagues, a metro map of what a Rust developer might go through. They might start with testing, then maybe they might try some sanitizers, they might try fuzzing, and then they might say, oh, let's go to let's go towards more of the formal world. And they might try some abstract interpretation. They might try some model checking. They might try some specification and verification of the specifications. And this talk is about Kani, which is our tool and sort of the bit of the Rust ecosystem that we're focusing on. And so one of the things that we're very interested in talking about is sort of how this whole fits together and how we can make sure that we're interoperating with all the other parts. But this is what we're working on, and this is our bit. So I'm going to start with a demo. I think that's the best way to show what something is. And can everybody now see a VS Code instance?
I can at least.
Okay. And let me know if this font size needs to be increased. So this is a simple example. This comes actually from the Rust documentation. And this is a rectangle class, right? It's a very simple class. It has a width and a height. And it has some predicates on it. So there's a predicate, for example, can hold, which says if one rectangle is larger than another rectangle. And there's also a function, stretch. And so stretch takes a rectangle and it takes an unsigned factor, and it stretches the rectangle by that factor. And so the question is, what are some properties that we might want to be true of a stretched of our stretch function, and how would we test them? So if you're a Rust programmer, the first thing you're probably going to do is you're probably going to write a unit test like this, right? You'll write mod tests, you'll write hash test, and then you'll write some concrete values, and you will check that if you increase by a factor of 2, you should get a larger rectangle than you had before. Okay, and so that's sort of the first thing that a Rust programmer might do. The second thing is, let's say, okay, well, you realize that concrete values are unsatisfying. So maybe you'll actually write a prop test. And so a prop test, I'm hearing a lot of echo right now. Thank you. So a prop test is like a regular test, except it takes these any parameters, which represent random values that allow you to search the search space. And so this is a form essentially of directed fuzzing. And so you could write the same test as you had with the unit test, but now instead of saying, width is a concrete value and height is a concrete value, you take these random values. And we can actually, this is the way this is set up, we can actually run cargo test. And in a couple seconds, it runs both the unit test and the prop test, and it comes back that there are no bugs. So this is great. We're all happy, and we can go home and drink our lattes or whatever it is that we do after we finish our coding. But let's say you want to go a little farther. And the idea of RMC is to be a smooth glide path from the testing and specification that developers are already doing towards something more formal. So remember what that prop test looked like. In fact, I'm going to open that on the right so you can see the prop test. Here's the prop test that the user wrote. And now here's a Kani proof. So here's what we're going to say. We're going to say, build an object. And we're going to use this Kani any operator, which looks like the prop test any operator, except for one difference. This any operator says, give me an unconstrained value. And so we're going to say, let's build a rectangle, give it unconstrained width, unconstrained height, an unconstrained factor. And then now let's assert the same property we had in the prop test. So I hope you can see that this is a fairly simple glide path from writing a prop test to writing something more formal, where we're actually going to solve this with a solver. And let's see what happens if we actually run this through the solver. It's going to take a few seconds to run. And in a second, it's going to come back with a result. So this hopefully, now I'm worried about, oh no, we have demo disease. Here we go. Took 17 seconds to verify. And we have an HTML report, which tells us, which we can look at and see what went on. The HTML report says, oh, there's actually 2 errors that happened on line 77. And the particularly interesting one is this assertion failed. Larger cannot, in fact, hold original. And one of the nice things about CVMC is you don't just get an error report, you actually get a concrete trace. And in this trace, you can see every assignment that occurred at the mirror level as we went through the program, which is large. But the key things that we care about are, okay, what was the width? Well, the width here was, this value 114,000 something. Okay, and what was the length? Or the height, sorry. The height was 0. And what was the factor? Well, the factor is, this very large factor here. And if you stop and think about it for a second, let's go back to the definition of stretch. If we have a height of 0, then the rectangle has an area of 0. And so no matter what the factor is, a new rectangle will not be larger than the old rectangle, because the new rectangle will also have an area of 0. And so in fact, you can run that, you can fix it, then you find out that also, the width has to be non-zero and the factor has to be strictly positive and non-zero. So we provide a Kani assume operator, which users can use to assume various predicates. And if we rerun the fixed one, we'll see it will run for, again, a few seconds, and we'll get back a result that will tell us verification successful. And if you want to scroll up, you can see all the different checks that we did. Okay, so that's a quick demo. Celina's going to get into sort of more details about a cooler demo, but that's a quick demo of what Kani is and how it works. And the thing that we're sort of, I hope you can get away from this, is that we're picking a very particular space of the REST ecosystem to be our initial user, right? And so our goal is we start with who is our user, and we work backwards from how can we best provide value to that user. And so in our case, our initial user is systems programmers. That's who, in our experience, we found a lot of success adopting these kinds of formal techniques. That's who we've been working with. That's who we've been consulting with as we develop Kani. And so as a side note, if you want a great, somewhat hilarious article about what systems programmers think and care about, I highly recommend this one by James Mickens in a Unix publication. So now that we have systems users as our target, that really says some things about what we need to be building into our tool. And in particular, verifying REST systems code requires bit precision. So we have to have bit precise code. And here's a simple example. This is from the Rust standard library. And this is the OS string class in the Rust standard library. And if we look at the comment on line 99, we'll see that the standard library actually relies on the OS string being layout compatible with slice. And why do they care about this? Well, systems programmers really care about low-level performance. This is something that's going to be used potentially in critical loops of other code. And if the two are layout compatible, they can just do a transmute instead of needing to do a clone and needing to copy any data. So this is a big advantage when you're writing code like this, but it also means that in order to verify the OS string systems library, you need to be able to understand layout compatibility. In fact, in code that uses transmute, you often may even need to be bit precise between the bit representations of different types. So you require bit precision in your object representations and layouts. Systems programmers require the ability to verify unsafe operations. This is from an open source transmission protocol implementation. And so this is some code that is running in the inner loop of the transmission protocol. And in that case, they do not want, right? They care about cycles per byte very, very deeply. And so it is worth it to them to do a get unchecked when you're operating on the slice, because avoiding that, that check really improves the wire speed of the protocol. Now, in some cases, obviously, the Rust compiler will allow these checks. In this case, the while condition is a little too complicated. The compiler doesn't yet allow it. So they have to use the get unchecked. And you'll notice here on line 34, they have a debug assertion. And that's great because they know the property that makes this safe. But of course, at runtime, they can't check it. But if you could model check it, if you could use a verifier to prove that this property holds, then you can get confidence in your unsafe operations. And Rust systems programmers really care about precise models of the heap. So this is some code from a virtual memory manager from a Rust hypervisor. And so this virtual memory manager is actually handing out, right? It has user code, it has user memory, which is some big chunk of bytes. And it's handing out slices to those bytes, which then the user code will interpret as various Rust objects. Right? So we need a way to actually precisely model the heap and to say that even though the surface level Rust thinks it's dealing with non-aliased objects, we're actually handing out objects that may alias, and then we need to make sure that the code works correctly even in that case, and that the protocols that are in place to prevent aliasing are actually doing the right thing. So taking a step back, right? So Rust programmers care. So we're trying to build a tool specifically for Rust systems code. And we'll talk about some of the challenges there, but it means that a lot of the really cool techniques that some of the other people in this group are using, we can't take advantage of because some of the safety assumptions that Rust applications programmers, for example, rely on are ones that must be guaranteed by systems programmers and cannot be relied on. So what are the properties that we check? Well, the first thing that we do is we check a bunch of we add a bunch of automatic checks for sort of standard memory safety and undefined behavior properties. So we check for buffer overflows. We check for unsafe use of pointers. We check for division by zero, pointer arithmetic, and arithmetic overflows. And those you get for free. If you run Kani on your code, we automatically will insert and check all of those properties. Now, it's important to notice that this does not yet cover all of Rust UV. So for example, we don't check type safety. So someone can do a transmute and we will faithfully model that transmute, but we won't actually tell you if that was a legal thing to do in the Rust type system or not. We don't check for invalid bit patterns being written into objects. Rust has this interesting property where it is undefined behavior to write an invalid bit pattern to an object, even if you never read it, which is stronger than the UB in many other languages, which requires that the pattern be read. And we don't currently check for aliasing violations. We'd love to implement something like stack borrows, but that doing so is future work. And in fact, in general, checking for all UB is hard because, yes?
Sorry, Daniel, there's a question from Ralph Young asking about uninitialized memory.
Yes. So that's a great question. And that sort of goes in some way similar to the invalid pattern. So what we do currently for uninitialized memory is we assign it a unconstrained value. So if you're used to sort of an LLVM model, uninitialized memory would get like a non-deterministic value, but would not get a poison value. Adding poison to uninitialized memory is something we would like to do, although we're going to need to experiment and make sure that that doesn't break other things. But yeah, uninitialized memory, we could model that by poisoning it. That's not something we currently do. So we will detect, you know, if your uninitialized memory has invalid patterns in it that causes problems later on, we'll see that. But the fact of reading uninitialized memory, we won't catch. Was that your question?
Yes, thanks.
Yeah. Yeah, and this warning is directly from the Rust reference. It's this big red box in the Rust reference that there is no formal model of Rust semantics, which I know some people in this room are working on. And so we actually cannot ever say right now that we have checked all Rust UB, because we can check for all the Rust UB we know of, but that's in fact as strong as guarantee as even the Rust specification can give us right now. So in addition to the automatic checks, we also allow users to check assertions by adding assertions to their code, and we allow them to check object invariance. And that's something that we found was really valuable on the C side. Is if for an object type, you specify a correctness property, and then you show that all functions that operate on this type maintain this correctness property as long as they are called with an object who has this correctness property. You can do a form of modular verification just using these object invariants. And so we've actually found that these C programmers have gotten quite far with this in some cases, and we're hoping the same will be true for Rust. And so a little side note again, sort of in terms of how we think about who our users are and how we try to serve them. So a couple years ago, we published a paper at ICSE on model checking in the software development workflow. And so this is really both a report and experience report, and also some methodology that we developed about how we found that industrial programmers most benefited from using code level model checking. And in particular, I highly invite you to read the paper, but 3 sort of key takeaways are that it's really important to use artifacts that fit within the developer's workflow. So writing specs in their language, right? So if you saw the spec that we wrote, it looks like a prop text, right? And this has pluses and minuses. It's a lot less expressive than, say, a Crusoe spec could be. But on the other hand, it's a very slight glide path for programmers to use it. Embedding the specs in their code and actually encouraging them, in addition to formal methods, to add the properties as asserts and then check them at runtime, we found both really helped programmers understand these, and actually was very valuable in terms of catching bugs up and downstream of the libraries that we were verifying. And this is really a key one. Proof should be able to run in continuous integration, right? Because if you do proof on a piece of code, you've proven that at that moment, that code did the right thing. But you still don't know, you still haven't provided long-term value to the customers because code evolves over time. And so if tools are designed to allow them to be easily integrated in continuous integration for the projects that use them, then it really helps the developers because they can move faster, knowing that at every commit, their proofs are still checked. And it helps the users of those programs because they can see that the version that they are running was actually formally verified. And so now I'm going to pass it over to Celina to talk about some deeper and more cool ways of using Kani. And this would be a good time for any questions while we are handing over.
So I actually have a a quick question.
Go ahead.
In your experience, have you found that there are difficulties with this CI integration of your proofs? In that, have you had any issues with sort of dealing with code evolution? I assume that proofs in Kani/CVNC are fully automatic and there's no user interaction to guide the solver along, but how common is it for, I guess, a minor or seemingly inconsequential change to just cause, tedious breakage in the proofs where nothing deep changed?
So we've not found it to be super common on the repositories that have used it. So again, our experience here is on the C coding side, not so much the Rust coding side yet. Things that there's some places where the ergonomics could definitely be better. So for example, if you're using loop unwinding, you have to give unwinding bounds, and then sometimes people will like rename a function and suddenly all of the things vanish. Or sometimes, and then the harder thing that happens is sometimes people will make changes and those kind of changes tend to be pretty easy for downstream users to just fix themselves. The harder part is if someone makes a change and it causes a performance regression, right? So someone uses a different data structure and suddenly something that used to run in like 30 seconds now takes an hour. That's not something that's going to really work in CI. So that's been the place where we've more needed to do proof maintenance. But the proofs themselves, I don't think it's much more work than, for example, maintaining a test suite when the code underneath it changes, because of sort of this design of it being very similar to a test suite.
Yeah. And if we have time for another question before the demo, I was also wondering, you showed us this trace that's generated, which seems to be mostly mirror level output. Have you explored either how to resugar this into sort of Rust level output, or even more generally, I noticed that it seems like when you show the values of different structures, it seems very different from what you would expect using Rust syntax. Have you explored how to present this in a more readable format for Rust developers?
We have. We've actually even done a little bit of work, sort of a proof of concept of providing this as a debugger input so that you could run your VS Code debugger and see the values and click through them. Now the step from proof of concept to something that works reliably enough to inflict on users, offer to users, is there. But that's something that we have seen looks very promising, right? Users are already very comfortable with debugging using a debugging interface. And all of the information that you need for a debugger is there in the trace. It's just not surfaced, perhaps in the best way. And so, yeah, it's the trace right now is something that like a formal methods person who's used to reading model checker traces can probably look at. But and one difficulty is that, as Celina was talking about, we work at the MIR level, and we've already lost a lot of information. I don't know. I expect a lot of people in this room have looked at MIR that comes out of even very simple Rust, and it's full of temporary variables and casts and all kinds of things that just don't appear at the surface syntax. So if you're starting with MIR and that is your source of truth that you're verifying, you end up with a lot of stuff that happens under the hood that you don't see in your surface syntax. And sort of how do you show that is an interesting open question.
Yeah. Thank you.
Okay. Hope everyone can hear me. So right now, I would like to talk a little bit about how Kani can be used to check for vulnerabilities. For that, we're going to use a well-known bug that happened on the Rust standard library. This has been documented in the CV database, CV stands for common vulnerabilities and exposures. What I really want to focus here is in the description is that one, this was a buffer overflow vulnerability. Two, it happened in the VecDec data structure that is available on the Rust standard library. And three, that it happened in the reserve function. So before I jump into the issue, let's talk a little bit about what the VecDec is. So I don't know if everyone is familiar with this. I wasn't. So the VecDec is a double-ended queue that is implemented with a global ring buffer. What does this mean is that you can push and pop from both ends, and you can grow that structure. So to implement that, the standard library relies on an underlying vector as the buffer, and it has two markers, a tail and a head. The tail points to the front of the queue, and the head points to the back. So you can see here on the side that we have, this is how kind of you can see a possible representation when the VecDec has a few elements. It's interesting that the tail will point to the first element that you can read when you do a front, and the head is the points to an empty element that would, that position would be where you would insert any element when you push back. So how do they represent empty and full? It's the interesting thing here is that empty header and tail markers, they're pointed to the same position. That means that VecDec is empty. But for full, they're basically adjacent, where the tail is the head plus one modulo the size of the raw vec, the buffer. So with that in mind, what happens is to represent full, this VecDec capacity is actually the same is the capacity of the underlying buffer minus one. So if you have a buffer size 8, now your VecDec capacity is actually 7. And that's for the representation. So let's look at the proof harness. Let's look a little bit at the code here. Before I go actually to the proof harness, I want to show what the reserve function. This is the function I mentioned that where the bug happened. Reserve is a function that you ask for additional capacity. So it's like, I want to make sure that this VecDec can fit this amount of elements if inserted without having to regrow. So here I wrote a small, simple proof that verified that the request to reserve space that is already available should be an OAuth. So if I have capacity of 7, so I start with an empty vector of empty VecDec that has a default capacity of 7. So I just use new here. I insert an element, and now I want to make a reserve request for something that is available, because I want to check if there's a OAuth. So I do my any request here, and I request that I want any value that is less than or equal to the available capacity. So I use an assumption to make sure that any is actually constrained, and I call the reserve. And at the end, I assert that the capacity of this VecDec is still the same as when I started this harness. So let's look what happens when we run Kani. So it fails. It fails if you look at, it shows all the properties that succeeded. And you're going to see that it failed here. And the assertion head is actually should be less than capacity. And it fails in the handle capacity increase function. So if we go back into the code now, and we open the VecDec implementation, I did forget to mention that this VecDec is a modified version of the VecDec that has the issue, because this issue has already been fixed. So if you go now look at the VecDec, this function is the one where the assertion failed. So if you look at this handle capacity increase, it's basically handling that things got reallocated. And it's called unsafe because it trusts the capacity. So this is where it failed. But what does this mean here? So in the end of this function, it actually checks for the invariance of the type. And this is the check that failed. That for some reason head was now was bigger or equal to the capacity, which means is a buffer overflow. It's pointing outside of a buffer. So now we know this. How do we debug further? So as Dana showed you, we have a trace that Kani generated. I already generated a trace for sake of time, and I'm going to open here for you. And I also grayed out. It's a very big trace, so I already marked the important bits of the trace. So as I mentioned, the vectec starts with capacity 7. And now I want to look at the reserve function. So as I said, this function is being called because there was an increase, but we were expecting no increase. So now if we go into the reserve function, I also annotated the code here from the values of the trace. So we can see that this reserve will call with value 3. So it's asking for 3 elements. So that should fit in this vectec. And what's happening here is that we do all the calculations, old capacity, use capacity, counting the slot that the vectec needs to represent empty and full, to differentiate between empty and full. And now if you look at the if condition here. So as we said, this function is being called, which is surprising, should not. And now if you look at this if condition, this is the interesting bit. The new capacity is being requested as 8, and that is the underlying buffer capacity. But self-capacity is an actual method that asks for the vectec capacity. So the vectec capacity 7. And that's why it's misleading and it's a bug here, that it thinks that the new capacity requested is actually greater than the current capacity. So what happens if we fix this? So let's fix this. Let's just use the old capacity, which is the actual underlying buffer capacity. And now we can run cargo Kani again. Let's go back. I fixed it, and this now succeeds because that property, if you look, I can find a property here. So you're going to see that a lot of properties now are unreachable, and that happens because that code is no longer called. So you can see all these unreachable functions, including the one that we had before. And it's because this if now cannot be taken because we are in a no-op state. So that's our little example. Let's go back to the slides. Okay. There we go. So just make sure, show you here. This is the actual fix that was applied to the standard library. This is the fix for this issue where the capacity was the wrong method. Really what we wanted was the underlying buffer capacity. So that's our little demo on how Kani can be used for these. And it's a real world example here. It's kind of cool. So now I want to talk a little bit about what happens under the hood. How is Kani implemented? Okay, so this is our high level flow of Kani. Kani will take Rust's crates or packages. Also, we also accept cargo. We support both standalone Rust calls the same way as cargo. We take Rust projects as input. We have a compiler module that will compile that into our IR. The IR here is a go-to program that we give to our model checker. The model checker is CBMC, and the model checker will check whether the model is successful or fail. So it will check if the properties in the model succeed, or if there's any failure, it will produce an optional trace. So diving deep a little bit on the Kani compiler. This is the bit that most of our work goes into. What the Kani compiler does, it does two main things. One, it will instrument the code with verification checks that Daniel mentioned. We check out for overflow, arithmetic overflow, and division by zero, and a lot of other things. That happens, a lot of it happens in the Kani compiler where we instrument it, but we also do the compilation from Rust to go to program. And to do that, we developed a custom front end on the top of the Rust compiler. So the Rust compiler, we use it as is, as just the libraries of the Rust compiler. And we also inserted now a custom Go-to-C codegen that will translate into Go-to programs. So what happens here is that we will translate the mir, which is the mid-level intermediate representation, into Go-to programs. And that's why Daniel mentioned before. So for us, mir is the source of truth. So a lot of things you're going to see in a trace, the level of details, the level of your B's, it will come from whatever comes from the mir. So let's talk a little bit about the model checker. So underneath the hood, we use CBMC. CBMC is a bit precise model checker, is a bounded model checker developed for C and C++ programs. It verifies memory safety, undefined behavior, uses specified assertions, and a few other checks. So some of the checks we have today actually comes from CBMC, which does their own instrumentation as well. And by default, uses a mini set solver that will do the bit vector propositional formulas. It will solve them, but it also supports SMT solvers. So CBMC, the way CBMC was developed, as I mentioned, was for C and C++ programs, and it's split into like three main stages. The front end is a parser that parses C, C++. It lowered that to Go-to program as a dir, and then performs symbolic execution, which is the middle layer, and then the back end is the decision procedure that will check whether the formula that was generated by symbolic execution holds or not. And that's when it gets the failure. And the neat thing about CBMC is that it also, the parser can produce a file for intermediate representations, and the symbolic execution, which is the mid layer, can consume those Go-to programs. And that's how we hooked up Kani here. So we basically removed the parser and we hooked up into the Go-To program layer, and we used the symbolic execution and the decision procedure. So I would also like to say that we are open source. We welcome contribution. We welcome, please go and try it out. Here's the link for our project. If you have any questions or if you find any issue, please file a bug. Don't be shy. And just to summarize,
I'm sorry, we have a quick question if you have time to answer it right now. Pointer Bender asks, are there any behaviors undefined in C, but which are defined in Rust? And can Kani report false positives because of that?
That's a great question. I can give you an example of something we've been working on right now. One of the interesting things that we've been working on right now is pointer arithmetic. So for C, it is undefined behavior if you go outside of the bounds of an object of a pointer. While for Rust has support for both. Rust has an std function that allows you to add. So if you look at the add functionality, it behaves like the C. If it goes outside of a bound of an object, it does have a UB. But if you use wrap add, for example, you can go out and in and back into the bounds. The important thing is by the time you dereference, that pointer has to be valid. So it's a very interesting thing. And the way we're modeling today is we're modeling like C. So we need to, that's something that we are working on a fix, which is for some operations that would actually cause a false positive. Does that answer the question?
Seems like it does.
Okay.
Yeah.
Cool.
And I also had
You had a question?
Yeah, I had a quick question earlier. You mentioned that you have a custom front end for Rust. By this, do you mean that you have that kind of uses a Rust C driver, or do you somehow modify the Rust parser or the sort of Rust input
Great question. I always get a bit confused because that's kind of a terminology from the Rusty. That just means we have our own driver. So we
Okay.
have our own driver that have, because we can configure the code gen stage with different properties, with different arguments, and that's all it is. So we do use the Rusty driver as is.
Okay.
And
And I'm sorry, but it seems like the questions are pouring in. There's a
it's okay.
follow-up. There's another question from Timothy Reed. Has Kani been used for industrial Rust code? And if so, can you say what kind of application and its rough size?
We're just starting Kani. We have a few use cases, but we haven't been fully adopted yet. We have a few internal use cases, but that's about it. I don't know if Daniel has more insight on that. Daniel?
Yeah, I think that's accurate. So we have some use cases where we're sort of like playing around with it, but nothing where it's actually been adopted and being used yet. But that's something we're actively looking for, both internally and externally. If you know of any Rust projects that you think would benefit from this, put them in touch with us, and we'd be happy to talk to them about using it. Yeah, we've been mostly focused right now on building on the stage one of sort of building the tool to the point where we can use it for industrial code. And then stage two will be taking the customer feedback to deal with any pain points that people run into.
Okay. Any other questions, Xavier? Or
No, I think that's it for the moment.
okay, so
I would have a
let's
question if that's okay.
Yeah. Yeah,
So that's a really nice case study with this VEC deck, given also how low level all of the operations or all the low level unsafe stuff. I'm wondering on which level basically you're modeling this, like how far down, if you go into the implementation of copy non-overlapping and all of those library primitives, how far down do you actually translate the Rust code versus insert some kind of model, whatever that would be, of what the Rust code is supposed to do?
Yeah. So for copy non-overlapping, what we do is we model that into a mem copy, and use CVMC has a built-in C library. So we use I think it's mem copy, not mem set. I'd have to double check that. I think because overlapping would be mem move and non-overlapping would be mem copy. Yeah. So we model it as a mem copy, and so it's doing a precise model of what a mem copy would do. But that's including the non-overlapping checks. But yeah, we assume that there's sort of a C standard library that you're going to lower into.
Okay, yeah, I mean, I think copy non-overlapping is also an intrinsic in the Rust compiler, but there's other functions like swap, for example, which actually have non-trivial implementations in libcore. Do you aim to actually like implicitly also run and verify that code, or do you also use models for that?
So that's something we're going to have to see a bit. So for intrinsics, when we hit the intrinsics, we just provide an implementation for those intrinsics. For stuff in the standard library, the goal is to start by just going with the implementation in the standard library, but to provide mechanisms and possibly standard stubs for some of this code, right? Because sometimes the standard library code does things that are good for performance, but very bad for verification.
Yes, so, swap is one of these examples because it like actually swaps data in like chunks of 8 bytes or some weird nonsense like that, which Miri wasn't very happy with one of the implementations there. So that's why.
So it's something where we could model that because we have the bit precise backend, but on the other hand, your performance would probably fall over. So unless you're dealing with code where you expect it to really matter, you would probably just use the stub there and just say like, treat it as the operation, not as the particular implement, like optimized implementation.
Okay, makes sense. Thanks.
Okay, if no further questions, just want to summarize. We can open for more questions at the end. Just want to summarize a little bit of our current experience is that we have been developing Kani with system programmers in mind and their needs. So the need for bit precision, for precise modeling of the heap, and a precise modeling of unsafe operations. We also focus on integrating the Kani into the developer workflow. We try to give the proof harness that unit test, prop test-like feeling. We allow users to run Kani via cargo or via standalone Kani, and we provide concrete debug traces. We also build on the top of well-established tools. We use the Rust compiler to do the lowering between Rust into Mir, and we use CBMC as our bit precise solver. And you're welcome to contribute, and we are also hiring interns. And if you know anyone that is interested, or if you're interested, please feel free to contact Daniel. Here is his email. So yeah, let's open for more questions if anyone has any.
Sure, I will have another question. I'm wondering what you're doing with respect to data layout, in particular fancy kinds of data layout like enum niche optimizations or niche or whatever the pronunciation is, optimizations. Is like, are you modeling, I guess since you're working on Mir, you pretty much have to model them accurately.
Yeah, we model them, and it turns out that getting layouts right is surprisingly tricky.
I'm not surprised.
Because but yeah, we, as best we know how, we model the layouts, and do things like niche optimizations, and and then you have to, and all of that. So something that would be very helpful would be if there was actually some sort of a document about layout, and for example, like what was guaranteed by the standard, what is considered implementation defined, what is considered undefined. That's something where we've sort of often had to backtrack it from saying like, okay, well, this is what the compiler does, and there seems to be code that relies on it doing this, so I guess this must be considered to be spec.
Well, if that code is in the standard library, then that like basically standard library reserves the right to exploit internal implementation details that might or will change. But yeah, I guess that would have been my follow-up question. Like, do you want to, or do you have the, like, is this tool able to detect when code relies on layout details in ways that it shouldn't? Like, I don't know, the order on fields in a wrapper Rust or things like that. Because if you're just strictly on the Mir level, this is kind of defined, but of course it's not actually defined in a fixed way and could change with any compiler upgrade.
Yeah, so there's a couple places where we would want to look for that. One thing we could do is say that the code that tends to care about that, right, it's really sort of when you're doing transmutes and when you're doing casts, that this stuff tends to come up. So we could say, if you do a transmute on something and at least one side does not have a defined wrapper, then we should warn and say you probably shouldn't be doing that. In fact, that's something I'm surprised doesn't happen just at the Rust compiler level. Like that seems like a lint that probably should be there for transmute.
Yeah, I think
I
talked about such a lint already, like in 2018 or something, and I'm not quite sure what happened to the lint. But
yeah, the other thing that I talked to Felix about at one point was this idea that the compiler could itself fuzz layouts a little bit, right? So you could have the compiler sort of like randomly insert additional padding or reorder fields. And that's something technically, I guess we could also do, but would be probably better done like at some compiler high-level pass to make sure the compiler hasn't baked in any assumptions about layouts by the time it gets to Mir.
I think dash C
but that would be-
randomized layout exists now.
that would be something we could run under and then see, you know, can you still prove all of your code if you pass that? That'd be a useful thing flag to offer, yeah.
Yeah, I think randomizing layout is a feature now. Dash C randomized layout or something like that. Not sure how much it randomizes, but yeah, that's useful for Miri, and I guess it's useful for you guys in the same way. Cool.
All right. Are there any final questions? Oh. I think there are some questions for your article, Daniel.
Yeah.
And
yeah.
And I think
someone posted it, yeah.
I think Yusuke may also have a question.
Yes. Can I ask a question?
Go ahead.
So there are some Rust specific features that C probably doesn't have, like closures and trait objects. So are you planning supporting them, because they are quite interesting in actual development?
In fact, we're going to be presenting a paper on supporting closures and traits at the upcoming ICSI. And
Really cool.
there's if you look, you can find the preprint. If you look on Alexa Van Hadam's page, she was an intern who's Nathan already posted the preprint. Perfect. Yeah, so if you want to read about how we handle those, that's there. And if you have any questions, reach out. Just a general comment, probably one of the best ways to contact us. So either, I passed it my email, and also we love contributors to our to GitHub. So if you use the tool, if you run into any issues, if you have any stuff, just post a GitHub issue, and that's probably the best mechanism to contact us about anything related to the tool.
Cool. Thank you.
All right, a second call. Any final questions? And if not, then I'd like to thank Celina and Daniel for their presentation. It was quite interesting, and I think I'm quite interested to see where Kani goes. And the recording for this talk will be available on YouTube, hopefully by the end of today. And I hope to see everybody back in a month for a talk on ferrocene.
Thanks, everyone.
Thank you, Xavier.
Have a good day, everyone.
Right.
You too. Bye.